Modern language models run across tons of GPUs, all connected in complex ways. Our goal is to make sure data moves through them as smoothly and quickly as possible, so everything runs faster and more efficiently. Every time you use a model, it's like setting off a massive group chat between GPUs, exchanging data between one another. Often, that back and forth is the real bottleneck, not the math. Think of data like water in a pipe. Latency is the time it takes for the water to start flowing. Bandwidth is how fat the pipe is. Together, they decide how fast we can move. In deep learning, no GPU works alone. Collective operations like all-gather are how they collaborate, whether it's sharing gradients or syncing predictions. These operations are at the core of all AI pipelines. The models we all use and love are built on enormous compute clusters. In these networks, poor communication planning can cripple performance. You can't just hope it works, you have to engineer it intelligently. Imagine hundreds of drivers rushing toward the same road at once. That's what training looks like at scale. We need something like Waze, not just for one packet, but for thousands moving together. Well, we built that Waze. Given the network and the task, our system finds the most efficient path for data, like a traffic planner for distributed AI. To tackle this, we used a mixed integer program, treating each decision as a variable, each network limit as a rule. It's math meets networking, solved with industrial-grade tools. We're not just making things faster, we're making them smarter. Our method helps teams simulate and refine communication strategies before deployment, reducing trial and error, saving compute resources, and avoiding costly bottlenecks in production. Let's see how our optimizer routes data. In this example, each link in the network has different latency and bandwidth, making routing much harder than in a uniform setup. And while this case is simple, our model can also handle topologies with switches and even failures, just like in real AI clusters. Instead of relying on random or greedy paths, the optimizer plans each transfer step by step, balancing traffic, avoiding overloads, and minimizing total time.